accomplished AI researcher and entrepreneur whose work is at the forefront of leveraging cutting-edge technologies to solve real-world challenges. An alumni of IIT Delhi, Omkar expertise into spans graphic neural networks and generative AI, where he applies his deep technical knowledge to create sustainable, transformative solutions. So today, Omkar will guide us through an exciting masterclass titled Balancing Skepticism and Innovation, the intersection of entrepreneurship and AI. So I'll request Omkar to spread some light on some use cases where we can use generative AI and new age technologies to solve for some financial problems specifically, which he thinks of. Over to you, Omkar. Yeah, thank you.
Thank you, Abhishek, for that introduction. So let me just start sharing my screen and let's go through it one by one. Just let me know if you can't see it. I'll again restart the presentation.
Yeah, this is
Can you see this?
Yeah, visible.
Okay, so the title of it is Balancing Skepticism and Innovation, the intersection of entrepreneurship and AI. And specifically, this is coming up because the current AI development, it is less on actual technology. It is more on hype cycle that a new technology is coming. It is going to be killer. You will see a huge amount of things happening. You will see jobs getting reduced. This is going to be as intelligent as humans, like a number of things that is coming. So as a founder or as an AI expert, how would you think about dividing them so that you can think about what is realistic, what is not realistic, what makes sense, and you should be able to divide it properly. So let me just walk you through our team. So Sanath is our CEO. I'm working at CTO. Srinivas is CPO, and there was one specific case that we thought was very interesting to what you guys are doing, and that was mortgage document processing. And specifically, this was some of the outsourced work that was coming from US to India, and what was happening is that there were huge documents up to 1,000 pages, and those pages were these documents were scattered in the sense that the agencies wanted, the clients wanted them to be indexed into smaller pieces so that all the loan application pages, they will be together. All the closing disclosures, they will be together, making sure that one page of one document is not moving to another page. And then, once you have done that, how can you extract that data properly? That is more of data extraction. So while we talk about AI, and again, there will be some general yarn that will be flowing in here, but you can put questions in the chat and I can address it as I go. But specifically, when we talk about being skeptical, is when you have large amount of data going in there, and that large amount of data could be, so it could be enough to train small language models, or it could be sufficient to look into a large language model. What starts happening is that data quality always becomes an issue, and you need to start looking at data very closely. So this is my estimate, is any data verified by human expert, it is always 95% correct. In the sense that in one pass, if there are 20 documents or there are 20 instances through which you need to parse, an expert needs to parse and understand what is going on, that expert is going to make at least one mistake. And that actually reflects through one pass, you should be able to get 95% accuracy. So what we were able to do is, we were able to index these documents at 98% accuracy, and extraction of it, we were able to provide a 95% accuracy. But again, this is 2024. What I'm talking about is 2019. We used transformer neural network, but very early forms of transformer neural networks, such as BERT and T5 kind of models, and we were able to extract data at very, very high accuracy. So what that also means is that when we talk about artificial intelligence is very hard by nature, in the sense when you talk about coding, then left-hand side is when you talk about algorithmic correctness, where you have some kind of bug in some kind of conditional statement. It could be a bug in function call. It could be bug in recursive computation, or either your seed case would be different. So either it is bug in implementation, or it could be algorithmic correctness. And in 2 dimension, you are able to understand what that particular problem is, what kind of solutions that you could build, and then you can move it to the bottom left kind of position where you say that solution is correct. But when you talk about AI, then it starts becoming very hard very soon, in the sense that you have one dimension that more talks about what kind of model issues that you are looking at. Is it overfitting? It is underfitting? Or is it correct? Or you look at algorithm correctness, whether that particular non-optimal data, is the learning rate correct? Are there gradients correct? Or you start looking at what kind of implementation correctness we have done. And there is another dimension, that is data, that we generally overlook. Is the data correct? And in these four dimensions, when you start looking at, then getting a correct solution, it's generally harder. So when we talk about AI, it is not just put your data in and run an algorithm. It is much more than that, and the amount of iterations that are required to fix one small issue, they could result in 4 or 5 iterations to come to an actual solution that you are going to get that you are going to deploy. So what that means is that there is 1x time that is required to fix a particular problem in your classical programming paradigm. It could be 4x, if not 10x time that you need to fix in these AI specific algorithms. And that you would see in different issues that have happened in international scenario as well. So again, what is the current landscape of AI in entrepreneurship? And again, some of this news is very old, up to 1 year to 6 months, but it is still relevant in the sense. So you had Sam Altman, who was seeking up to $7 trillion to reshape business of chips and AI. He went to Middle East asking for money to build this huge AI startup. Then you have Google CEO, when you had so when Gemini was launched with image generation, then you were getting very unrealistic kind of images, and that is what they tried to fix. So that was another problem that they came in. And again, Google being one of the gods of this entire AI world, they were still not able to fix these issues at launch or even after subsequent iterations. You had video generator models which were coming in, and now they have started trickling in. But when OpenAI announced Sora, then it started becoming it came as a surprise, because you are able to give a prompt, then it generates images, and with those images it is able to generate subsequent images, so that you actually have videos. Some of it has started coming into production, but what it does is that it tries to build physics into it as well, so that world level physics is possible. Then you have small language models such as Mistral, and companies such as Mistral. They are launching the smaller models, and they are able to come to a level where you are getting accuracy as GPT-4, Cloudy, that kind of level. So these different things are happening in international AI landscape. If you look at Indian AI landscape, you had Servam AI, which backed around $41 million in funding. They trained a small model, which they spent around $1 million to train, which is able to understand different Indian contexts, Indian context text, and then it is able to talk to you in that particular language, which was pretty powerful. And again, there was one failure that happened is government asks for firms to take permissions to launch AI model. That was just before the election, and government went completely. They took drastic steps, and that came as a shock to Indian community. So we are part of organizations such as AI for India, where we are trying to talk to policymakers. We are trying to talk to different stakeholders, where we are trying to build a consensus among these peoples and we are trying to build a different better AI models going ahead. But while all of this is happening, most of the AI startups which work in this particular area, they point to this particular article by Rich Setter. You can Google it. It's called as the bitter lesson. And what they say is that whatever amount of work that has been put in by an expert, given sufficient compute, a generic AI algorithm is going to beat that specific algorithms very soon. And this is the bitter lesson that went in very heavily. What that actually meant is that you just put huge amount of data, and then you just put huge amount of compute, and then AI algorithm will learn by itself. And on top of it, there became a hype train. It started pushing its hype cycle that all you need is data and compute and you're able to solve the problem. Probably you don't even need data. You can generate data, and while you are generating the data, it should be able to give you the model that you're looking for. Based on that, there were a few new. And can you see the screen, or are you still at presentation? I'm shifting between screens, so I'll have to stop. So I'm showing an article. Are you looking? Are you able to
Yeah,
see
yeah.
the
This
article, or
Twitter
is
lesson one is there.
no? So let me stop sharing. Let me again start sharing. So just give me 1 minute. I'm sharing entire. Okay, so can you see this?
Yeah.
Okay, so this is basically situational awareness. Just give me floating meeting address. Okay, situational awareness. The decade ahead, and this was released probably a month ago, where they were talking about GPT-4 to AGI, and how artificial general intelligence is taking the world by stride, and what they are talking about is OMs, is order of magnitude compute. So when they talk about this article, what they talk about is how much compute do you have to put to go to next level. So in this particular next 4 years, what they are saying that GPT-2 was 2019 and GPT-4 was 2024, and then they are talking about that how much compute they will have to invest. So currently, let's say if you have 1,000 computers running in the world, then you will have to put 10 to 4 computers, 10 to 6 kind of compute to actually reach to that level of newer models. And then there will be some kind of algorithmic efficiency coming in, and unhobbling. They talk about real reinforcement learning with human feedback, scaffolding, these kind of tools that will come in. But when you look at these kind of things, you have to be extremely skeptical, because it actually, this bitter lesson relies on is, and you can come back, so you can see the bitter lesson presentation now, right? Sorry,
Yes.
Abhishek, I'm,
Yeah.
okay. So when you talk about bitter lesson, then it just says that you just need data and compute. But where is data coming from? So amount of data that was on the internet, most of the models have already trained on it. So there is no new data coming in. It is now not coming in as a waterfall. It is just trickling down. So newer data is not being generated at that level. And again, there is an issue of, while the new data is coming in, a huge amount of data is again AI generated. So you are going into a completely, you are going into a state where model is again training the data, creating new data, and again learning on that data. That's not a good place to be. So while you're talking about something like bitter lesson, there have been more work have been done. So again, what my request to you is, when you look at these kind of articles, please be extremely skeptical about these articles. So this is one paper that came in 27 February 2024. The era of 1-bit LLM, all language models are 1.5 bits. So what this does is that it basically reduces 64-bit large language models to 32-bit, 16-bit. And again, this specific work is able to reduce it into 1.5-bit. So if your large language model is around let's say 10 GB in size, this basically reduces it in probably 1.5 or 1 gigabyte in size. What that means is that amount of memory that is required to run a particular a language model, it is reduced. But while that is reduced, here they were able to reduce the matrix multiplication operation into an addition operation. Now, while this happened, basically the impact of this particular piece is that you are able to run a small, or even a larger model, 70 billion parameter model, 100 billion parameter model, on your smaller computers, desktop computers. So when you look at a paper like this, and when you go back to something like this, where they are talking about you will need 10⁻⁴ more compute to actually go to a bigger model, you start looking at it extremely skeptically. Now let's start looking at another case. So this is first case. Now let's talk about the power of data itself. So this is another paper that was released by Google DeepMind. It was released on 7th of February. And they are talking about grandmaster level chess without search. And search is one thing that these people, the bitter lesson people, they have almost forgotten. So what happens in this particular paper is they were able to train a very small, and you can see over here, there are multiple parameters, but a 270 billion parameter model, where its tournament elo was 2,300, and it against humans it performed around 2,800 or 2,900 elo. But if you look at the something like stockfish. And again, it's not full on stockfish. It is being used at 0.05 second. It needs to make a move in 0.05 seconds. And this tournament elo, if Google's model's tournament elo is 2300, then this tournament elo is 2700. And again, you can see it is beating this particular model by completely. So again, but why is this happening? Like, why is stockfish still king? And when Google had all of their resources running, why Google's model is not able to understand all of this? The reason is, and if you look at this particular piece, this particular this particular table, you can see network depth at 8 parameters, 8 layers. The accuracy was highest. That was 81% accuracy. And when they increased the depth of neural network, that is 16, the accuracy actually came down. What that means is that even if you have infinite data, what that means is you're not able to reach to a level so your model will get saturated, even if you have infinite amount of data. And what that also means is that models which utilize search, such as DeepMind's, AlphaZero, these models will always beat the models which are using raw capabilities of neural network. That is something that these models are not taking into account. But while that is also happening, you should be able to see something like QuietStar, where OpenAI released a new model called a Strawberry codename, and and O1 preview is available, and it is using search in its inherent mechanism, where while generally a model basically predicts one token and there is just one thought process, they're trying to integrate multiple thought processes to actually give one particular prediction, and they're using search-like algorithm to actually get to the answer. Now, what that actually also means is, while we are looking at the press releases coming from bigger players such as Sam Altman and other bigger players in the AI industry, we have to be extremely skeptical looking at them, and we have to always think that is this, like, whatever their statement is it actually about humanity? Is it actually about technology, or is it about their next funding cycle? And we have to make a proper decision out of it. Next one, so how accuracies of different algorithms go. So I'll discuss a little bit about it. So this is a something called as multi-needle retrieval accuracy baseline comparison. And while you are in finance industry, you will see is you will have to extract a huge amount of values from different documents, and these could be if it is structured text, then good, you can extract it in a much more easier way. But when you go into unstructured text, then different small and large language models start they start coming in very heavily. So what you're seeing over here is a test called as multi-needle retrieval accuracy baseline comparison. And again, Gemini Pro is one of the big models that have shown very promising accuracy. GPT-4 also has shown very promising accuracy. But this particular paper came in not this one. This is a Reddit post. This particular paper came in a few days ago, and just give me let me just, how do I exit it? Yeah, I have exited. Let me just copy this particular paper and put it here. So this particular paper was used by Google to actually build their models where they are around 1 million tokens in length. So compared to what OpenAI is doing or Anthropic is doing, their context size is around 250 or 200,000 tokens. Google's model are able to process it up to 1 billion tokens. And the parameters they are using to evaluate their models, it's called as something such as needle retriever. And again, needle retrieval, it comes from a test called as needle in a haystack, where you have huge amount of data. For an example, this is called as multi-needle retrieval. So they have 1 million context length. In that, they put 4 random facts. And when they put 4 random facts, they try to extract 1 fact, 2 fact, or 4 facts throughout at a particular accuracy level. And you can see over here is while those context lengths at needle, if you have put 4 needles and you need to retrieve just 1, you can see the accuracies are around 100% to around 80% in different context lengths. When you go for something like needle 4 and retrieval 2, the accuracies drop down to 60% to 80%. And when you have two needles and you need to retrieve both of them, they kind of stay in this particular space. But specifically, if you look at, so there is another paper, let me just find out, it came in differential transformers. Yeah, differential transformers. So this paper came in a few days ago, it's 7th October. This paper actually created a completely different kind of transformers, where rather than having one decision criteria, it applied two different decision criteria, and with respect to that, they were able to report very high accuracies. For an example, you can see these different benchmarks. So you can see that a differential transformer is actually able to beat the normal models which are in production. But while that is happening, and again, you can see either it uses 38% fewer parameters in models or 36% fewer tokens in those models. But when you're looking at that particular data, they again talk about multi-needle retrieval accuracy. And again, they are claiming their multi-needle retrieval accuracy is n equal to 1, r equal to 1, something that I showed you earlier. But actually, if you go to definition of what this multi-needle retrieval accuracy means, so it comes from this particular GitHub repository, which is called as LLM test, needle in a haystack. And what they do is, the test is place a random fact or statement, that is what they call needle, in the middle of long context window, that is haystack. Ask the model to retrieve the statement, iterate over various document depths and context length to measure the performance. And when you are extracting on that particular level, when you think about difficult documents, such as financial documents, legal documents, or in my case, biotech documents, the needle and haystack, they have different physical attributes. In the sense, if I am putting a needle, which is the best thing to do in San Francisco, is eat a sandwich and sit in Dolores Park in sunny day. And if you put it into a financial document, which is a loan application, or if you put it in a legal document, which could be your standard services agreement, or a biotech document, which could be a publication paper, then it is going to stick out like a sore thumb. You are able to extract it very, very easily. So that's why these, again, the tests which are shown to you, where they talk about accuracy, which is coming to 98%. They talk about some of the work that is being done, where they report accuracy is 99%. These are unrealistic. So what that also means is that if even the bigger models are not able to achieve to that accuracy level, there is space for people like you and me to actually go there, do some real technical work and get the results out. So, and again, while that is also happening, you have to think about the pricing part that comes into it. So for an example, so the modules that we have available at, so the products that we have at knowledge.com, each of that module, if I go and use the standard large language model route, it would cost me around $90 million to produce a single module. But we already have 8 such modules already online, 8 more in pipeline. Something like that, you can't imagine with large language models. So while you're thinking about state-of-the-art technologies, always be skeptical that these large language models, they are claiming a lot. But while they are claiming a lot, what tests are they using to claim some level of performance? And what do those tests mean? You have to go into the actual references. You have to understand what that reference is, and is that relevant to your piece or your work? If it is relevant, and if at those benchmarks you're able to go to this particular depth level, I'm definitely sure you will see a lot of different spaces being created, which large language models or artificial general intelligence can't occupy that space. That is where you make money. And again, this is some of the newer work where, again, Cloudy 3.5, Sonnet, the kind of answers that it was giving, which is mostly irrelevant by now. Now, second one is retrieval augmented generation. And retrieval augmented generation, it's something that was in huge hype 1.5 years ago, 1 year ago, where what they do is they use an encoder-only model to take a context, convert that context into a set of vectors. And those vectors then, when they compare with each other, they are able to give the answers that they're looking for. And you would see, a huge ecosystem of different dedicated vector databases, vector search algorithm, it start coming in, and a huge amount of money was invested into it. But retrieval augmented generation, it does not work. And why it does not work? So I'll give you a simple example. So here is a simple example where I have 10,000 batches. Batches around 1,100 batches of 10,000 batch size each, and at each batch size, I ask that algorithm. So each of the context contains a publication, and from that publication, I'm trying to find name of the indication. And there is a small, tiny classification model which is sitting at the end of the extraction, end of this retrieval, and it is saying whether the given paragraph does it contain that particular disease name or not. And you can see in the only first batch itself, it gave very high accuracy. But as soon as you started looking at it, it dropped down, and the accuracy is coming around 5%, 10% of that particular retrieval. The reason that it happens, because number one, these RAG methods, they are they're probabilistic. They are not they do not give definitive retrievable, replicable work. Something like BM25 or BM45, the algorithms such as these, they're able to give something that you could replicate, but that is heterogeneous retrieval. What that means is that you have two sentences that you want to search, and the paragraph itself, it could contain around 1,000 sentences, and there is large amount of noise that is created by these 1,000 sentences that creates large amount of noise, which in turn reduces the quality of retrieval. And again, when you take something data that is directly pulled from these RAG pipelines, and then you put it into your large language model, it is more of a garbage in, garbage out problem, where you are pulling the data which contains huge amount of garbage by itself, and again you are able to you process it further, and it doesn't work. So be extremely skeptical for new age technologies such as RAG. I'm not saying that RAG doesn't work. I'm taking that I'm embedding based RAG where retrieval is heterogeneous, it doesn't work. So if you are searching for two-word queries, your queries are two-word in size, and your retrieval is two-word in size, it will definitely work. It will work at a very high accuracy. And again, these are very computationally expensive. They're not feasible for large, huge data sets. So think about, are there any traditional algorithms which could replace that, and you could get better answers. So something like transformers, it's some you have to start looking at skeptically. And I have shown you another paper where you are able to take 64 bit transformer and convert it into 1.58 bit algorithm. But while transformer itself is training on large amount of data, it actually follows, gives higher level of accuracy for the spots where it has large amount of data, and outlier is where it starts missing heavily. So you can see this is a transformer algorithm that I had trained for a hardware, a glucose monitoring hardware. It is inserted inside your body, it stays in your body. And you can see that, there are three different ranges where it was supposed to give very high accuracy. Number one is, hyperglycemic, normal glucose level, and hypoglycemic. And you can see that if you don't have data for outlier ranges, the accuracy for that outlier ranges is always going to be lower than what you have in your normal ranges. So you have to, keep something in mind is what algorithm are you using? Probably you don't need transformer. Probably simple linear regression would able to solve problem. Or if you are in confusion, just use something like XDG boost, and it should be able to solve your problem. Then again, decoder only model is something that you need to start looking at skeptically, because it sets up stage for hallucination. So this paper was published by Google in I think what was the date? 21st September 2023. And what they were able to see is that when they have task-specific models, those task-specific models, if they are using distilled data, where the smaller models are given a way of explaining that, okay, do A first, then do first, then they were able to see that a simple 770 million parameter T5 model, this is an encoder decoder model, it was able to beat a 540 billion parameter model very easily. So that is around 700 times model size reduction. So these things also happen. So when you look at the architecture of a particular model that you're using, you will have to think, choose carefully, and you have to use the correct model going ahead. Then large language models and lossy compression. So when you look at large language models, what they do is they take large amount of data, and they, in a way, they compress them in such a way that you can't replicate the compressed results. And that has been a fallacy of all of these large language models. So again, there was a case where New York Times it sued OpenAI, and latest they had some lawsuit that was brought against Perplexity. But while you're looking at these lossy compression models or large language models, question is that for the business case that you're looking at, do you really need a large language model? For an example, this ETS Zurich paper, it explains about exponential faster language model, where they were able to use around 0.3% of neurons, where it selected only 12 out of 4095 neurons, and it was able to achieve around 78 times speed up over a normal, simpler, neural network model. What that also comes in is that when you're talking about these large language models, maybe you don't need a large language model. For the case that you are looking for, probably you just need a tiny model which is able to, understand data properly and generalize much more faster, and you are able to address the outliers very quickly. Something like that would be very interesting. Another beautiful paper that came in is low resource text classification, a parameter-free classification method with compressors. This method doesn't even use a neural network. This method uses something like a compressor, that is a gzip compressor or a zip compressor. You can even see code over here. And it is able to beat neural network classification models by 2-3% very easily. And what it does is that, and you can see the results here as well, in terms of what kind of quality of answers that was seen. So if you look at something like sentence BERT or LSTM TF-IDF BERT, and they were able to reproduce it at 94% accuracy, 97% accuracy, and at different accuracy levels very, very easily. So what that means is that when you will be building your own models, when you will be actually training data, question is that do you need large language models, and do you need lossy compression, or can you just use smaller language models, or you don't have to even use large neural networks. You could even let neural networks go, and you could use something like gzip, and you should be able to get better results. Again, programming languages which are being used, they actually serve a lot of purpose. So Python is a go-to programming language for a lot of these different frameworks. And it has been because they are easy to use, they're easy to learn. There is extensive libraries, there are extensive frameworks, that is versatile, there is strong community support. But while you're using something like Python and you're building a prototype, you need to start thinking that whatever prototype that you're building, can that prototype be reflected on a production scale? Because in the state of the AI platforms and frameworks are being looked at, something that you are able to look into at a very small scale, it doesn't replicate at a large scale. So with respect to Python, the problem starts coming in because there are performance limitations when you host these different models, and you need to go through a huge dependency hell. You need to install these different Python programs. There is a global interpreter lock that basically stops multi-threaded execution of Python programs, or memory consumption issues starts coming in. So you need to start thinking that, do you need Python, or probably could you use something like C or Java-based support has started coming in Hugging Face as well. You should be able to jump to newer programming languages such as something like Rust. You should be able to use JavaScript in front end as well. You should be able to use something like Golang for all of these different programs. So question is that Python, should you start thinking about it as a de facto language, or should you think about other different frameworks to use it as well? Then PyTorch is something that is extremely well spread into ML community. Again, easy to use. There is a dynamic computation graph. there is a strong community. But issue is that what has started happening is lately PyTorch is being sidelined uh, because it is good for training, but while at inference, something like llama.cpp, it is able to beat PyTorch by a huge margin. There is a huge amount of performance overhead. So there you will find different examples of LLM.C or llama.cpp. People have handcrafted C programs where they are running these neural networks on a metal level. And what is happening is nowadays the ML is becoming more of inference heavy. That what goes in production, how do you run it in production rather than training heavy. So these models start having a huge amount of issues going in ahead. And again, NVIDIA GPUs, that is something that is you need to start looking at it skeptically as well. NVIDIA was one of the largest companies in terms of market cap a few days ago, and then it dropped down from there. But question is that do you need something like NVIDIA GPUs? Because something like H100 GPUs, they were extremely expensive a year ago, where something like Elon Musk or Oracle CEO, they had to go to NVIDIA CEO and they had to beg for those GPUs. But now you can rent these H100s at $1 per hour kind of price. And there are actual hackathons which are happening where they are trying to see if someone needs to train a GPT-2 kind of model, where 124 million parameter model, how much does it cost? How much should it cost to rent these GPUs? Current record is around $8. So a 124 million parameter model, you should be able to train in $8 compared to millions of dollars that were being spent three years ago. So in terms of the cost that you're going to put into while building internal infrastructure, you need to start thinking, whether you should be thinking about it. So our internal infrastructure that we use at Binomial, we do not use any GPUs at all. We use Mac and Max Ultra systems where we are able to get very high speed and very high performance, both on training and at inference. And again, cloud computing, you need to start thinking about skeptically, because now it was at that particular level where you needed, there was not that good internet available in different cities. Now that thing has gone. You have very good internet available. So, would you rather spend millions of dollars, in your case, thousands of dollars in cloud computing, or would you just buy a computer and get started? So again, there are ethical considerations, societal impact. We need to think about it. But coming back, I'll stop sharing. What you need to start thinking is that what is useful at your scale. If you are starting from a garage level, then you don't need expensive GPUs. You don't need out of the world large language models. You should be able to build your own algorithms, and for that you don't need to enter into neural network territory as well. You can use something like a gzip algorithm to build a classifier, build an extractor, and it works very well at 95%, 98% accuracy. So that was more of my presentation, Abhishek. If there are any questions, I would be happy to address them. Sorry, you're on you're on mute. Yeah, please go. Yeah.
Why are we going with addition while reducing the memory required? I think this is in the reference of the initial.
The first paper. Yeah. So generally what happens is that if you look at transformer architecture, the biggest bottleneck is matrix multiplication, which needs to happen at multiple times. So there are two different pieces. Number one is memory, because the large language models or the machine learning models that are being used in production, their issue is number one, compute, and second issue is amount of memory that needs to flow in and out of GPU. So when you reduce the size of the model, what that means is that memory bandwidth, it is efficiently utilized. When it is efficiently utilized, what it means is that you can run models much more faster. That is one bottleneck that is removed. Second bottleneck, that is compute. So when you remove matrix multiplication, you replace it with the matrix addition. What that means is number of flops that are spent on matrix multiplication, they go away, and you're able to just add it. And this is Microsoft model bitnet. You can look at. I think there are a lot of models which are in production in this particular question. Is there any other question?
No, not right now, but anybody has any question, we can bring you on the stage. We'll wait for 1 minute, Omkar, and then we'll conclude if there is no queries. But
Yeah,
could be looking ahead if you can spend, maybe give us what 10-15 minute slots, because we are nearer to the end of the hackathon. So there might be some one-on-one session which the teams would require. So maybe we
absolutely, absolutely.
for that. Uh,
That sounds good.
do we have any other question? I don't think so. So, Omkar, we can wind up then. Thanks for joining and guiding the teams. I'm sure once the team review the recording, we'll have more question. We'll reach out to you for the help.
Absolutely, absolutely. And please send if you send an email about different questions that students have, I'll definitely write back with
Thank,
respect to answers.
thanks, Omkar.